Okay, here we go. It's our last practice test tutorial for the year. Woo-woo! This is over exponential growth and decay. It's practice test 1. There is only one practice test. And this growth and decay section is part of the factors, rates, and initial values. There are only 4 sections on this test. So this is included in the factors, rates, and initial values. Okay, circle the appropriate description of each graph. I'm reading my graph from the left to the right, just like I read the pages in my book, from the left to the right, and I see that it's slow going. It's slowly increasing, and then it takes off. As you can tell, as we move from the left to the right, it is increasing in value, so that's exponential growth. On the other hand, as I read this graph from the left to the right, I'm starting up high, around 10, and slowly going down. My function is decreasing in value, and where it levels off, it's still decreasing. It's hard to see that it is, but it's decreasing at a very, very, very slow rate as we move to the right. But it decreased exponentially at first, coming down. So that's exponential decay, when our exponential graph is decreasing from the left to the right. This is also part of our first section of the test. Circle the appropriate description of each equation. I can tell whether it's growth or decay by looking at my factor right here. Is 5 over 2 greater than 1? Yes, therefore it is a growth, exponential growth. Remember we talked about in class, if our growth factor is equal to 1, there's no growth. If it's greater than 1, there's growth. If there's less than 1, there's decay. So 5 halves, if you put in your calculator, you'd see that's equal to 2.5, which that's definitely greater than 1. Over here we see 0.888 repeating, and we all know that 0.8 is less than 1, therefore it's exponential decay. 1 means no growth or no decay. Anything below 1, as far as the factor goes, means it's a decay. Anything above 1 is a growth. Okay, and then we'll have this part in the factors, rates, and initial values section, where they're going to give us an equation, and they're going to ask us for these things. So we need to be on the lookout for this type of equation right here. I'm going to rewrite it. Does it help if I rewrite it like this? There we go. That tells me that, first of all, when I look for it's a growth, right? So it's a growth. And my factor, remember I told you in class, it's a fact that this is my growth factor. Whatever is the base that's being raised to the x, that is your factor. It's a fact that 1.23 is a factor. Now, as far as the rate, we know it's a growth, and we say to ourselves, okay, how much above 1 is 1.23? And we can see that it's 0.23 above. So that's our rate. Our initial value, usually we're used to a number that comes right after the equal sign. When we don't see 1, it's because our initial value is 1, and we just don't write it. All right, so we look at this next one. We can tell it is a decay, right? It's going to be a decay because 4/5 is less than 1. So our decay factor, it's a fact that 4/5 is in my equation, so 4/5 is my factor. To find my rate, I'm going to say, okay, decay is whatever is below 1. So for our rate, we're going to find out how much below 1 is 4/5. And if you think about it, 1 minus 1/5 is 4/5. So our rate is going to be 1/5. Another way to get the decay rate is to just take 1 minus the decay factor. That will give you the decay rate. So whichever way you do it, you could do it this way with the blank, or for decay, you can say 1 minus the factor, and that will give you the rate. Okay, let's move on. Oh, initial value. Our initial value is the initial number that we see right after the equal sign, and that is 3. Okay, here we go. We know that 0.6 is less than 1, so it's a decay. We're dealing with the decay here. So our decay factor, it's a fact that I see 0.6 in my equation. I could write 0.660. It doesn't matter, whichever way you want to write it. And then when I talk about my decay rate, I say, okay, 1 minus what is giving me my decay factor of 0.6? And I can see that it's 0.4. Or if you want to do it this way, just with decay, 1 minus my factor gives me my rate. All right, so my rate's 0.4. My initial value is the number that appears initially right after the equal sign, and that's 0.75. Awesome, we're done with one section. The next section you'll see on the test, I believe, is your context section, and we started out with our unit teaching, looking over this. I taught it, and you guys really got it right away, and we saw problems like this. A Gila monster is about 16 centimeters long at birth. So right away we know initially, in the beginning of time, this Gila monster, 16 centimeters, we know that that's going to be our initial value. During the beginning of its life, the Gila monster's length increases by about 15% each week. So we already know that every good function starts with y equals. Sometimes we write f of x equals, but we're just going to write y equals. For growth and decay equations, it always starts with our initial value, which is 16. And then we've got our growth factor, because this Gila monster is growing, so it's going to be a growth. We need our growth factor, and then we have x for our exponent. And so how do we find the growth factor? Well, if you want to put 0.15 in, that's a good way to get it wrong. So let's do it the right way. I look at the percent, and I'm going to change the percent to a decimal. If I do that in my calculator or in my head, I see that's 0.15. That is the rate. That is the growth rate. It is not the growth factor. So we think about this. Remember, 1 stands for no growth, no decay, right? If I multiply my height by 1 every year, I'm going to stay the same height. And I am, because I'm not growing anymore. Well, at least not in height. So if it's a growth, we're like, okay, we're going to add to that 1 however much we're growing. So this Gila monster is growing 0.15. So that means the growth factor is 1.15, and we'll put that in there. So there is our function that models what's going on with the Gila monster. So then it says find the length of the Gila monster at the end of 3 weeks. So x stands for the time, right? X stands for the number of weeks. And so it's saying 3 weeks. So that means I'm going to take my equation and I'm going to plug in for x. I'm going to plug in a 3. And I'm going to pick up my calculator. I'm glad I have one close by because I can't do this in my head. And I'm going to put this in the calculator. I'm going to remember to use that up button to get up into the exponent, so I can put a 3 there. And when I hit enter, I get 24.3. 334, we can just round up to 3, or round off to 3. So that is, let's see, is that centimeters? Yep. In 3 weeks, this is how long the Gila monster is going to be. I'm not sure if the Gila monster grows tall or long. Is the Gila monster even real? I do not know. All right, so let's look at the next one. Sam takes an 800 milligram ibuprofen for her nagging backache. Every hour that the ibuprofen is in her system, a quarter of the medicine dissolves in her body. These are made up facts, of course. All right, so write a function. Every good function starts with y equals. Initially, once Sam takes the 800 milligrams of ibuprofen, that's the initial amount of ibuprofen that's in her body. Starts off with 800, and we know because we talked about this in class, and when we take medicine, it slowly dilutes itself within our system. It doesn't stay at 800 milligrams, or else all we'd have to take is 1 ibuprofen, and we'd be good to go for the rest of our lives, right? We'd be set. But no, it dissolves in her body. There's probably a better word than dissolves, but that's our initial value. It's going to decrease, right? It's going away in our system. It's not going to stay 800 forever. So we're going to have to find our growth factor. And so I see that it is it's a quarter of the medicine. So when they give us a fraction, when they give us a decimal, when they give us a percent, we need to stop and go, all right, what is 1/4? What is a quarter as a fraction? It is 1/4. But that's our rate. If they give us a percent or a fraction or a decimal, that's our rate. That's not our growth factor, or rather in this case, decay factor. So we have to stop and say, all right, so if we've got we start with 1, and the decay, it's going to decay by 1/4. right? It's going to go down by 1/4, so that means 3/4 remains over time, right? So our growth, or I'm sorry, our decay factor is 3/4. So what we're going to do is put this into the calculator. We're going to say, put the 800. I'm going to have to press pause because Kyle is here. All right, wait, pause. Okay, so where were we? A teacher just came to visit that I haven't seen in, gosh, probably 2 years, so that was fun. All right, but now I'm back. So we've got 3/4 is our decay factor. If we put 1/4 in, that's the amount that it's going down. That's the rate that it's decreasing, but we're really looking for what's remaining in the body. So think about it. That's why the rate is different than the factor. The rate tells you how much something is going down, but the factor tells you, well, what's remaining as this rate is having an effect on the body. So here we go. It says when there's less than 200 milligrams of medicine left in the body, it's safe to take it again. How long will it take? When they're asking us how long, we can't go ahead and plug 200 milligrams into the y and solve for x because we don't know about logs and natural logs yet. So what we're going to do is make a table. And we're going to start saying, well, you know what, let's find out. We already know that in the beginning, initially, there's 800 milligrams in the body. So let's see, after an hour, that's going to be what, 600 milligrams, right? I did that real quickly in my head. Hopefully that's good. I think I'm going to jump to 3 hours. I don't think it's going to be 2 hours. Let's jump to 3 hours and see what happens. So I'm going to put this in my calculator. Okay, that gives me 337. We're getting closer, right? Let's try a 4. So we'll go ahead and put the 4 in. Feel free to do this along with me. Oh man, it's not 4. Okay, how about 5? Let's try 5. Let's see what happens when we put 5 in. Maybe after 5 hours, it will dip below 200. All right, finally, that's 189. All right, so when there's less than 200 milligrams of medicine left in the body, it's safe to take it again. How long will it be before CM can take more medicine? 5 hours before she can take, or he, I don't know if this Sam is a girl or a boy, can take the medicine. Awesome. All right, before we head on to the very last part, which is, oh, well, no, before we head on to the next part, which is equations from tables, let's talk real quickly about a third type. We see that we had a fraction that we went ahead and, since it was decay, we subtracted from 1. And then the one before it, we had a percent. We changed a percent to a decimal. And we knew because it was growth, we added that rate to 1. There's another type, though, and I just want to remind you, wonder if it said something's growing at 5 times as much every minute. That's just when it says 5 times, 2 times, 3 times as much. Those are just your growth factors, straight up. That's what you're going to put in. We introduced that as a multiplier. That is a multiplier. You're just going to put that straight in. So I just want you to be reminded of that. All right, equations from tables. So we're looking for a few things. We're looking for initial value, and we know that initial value means in the beginning, initially, before time begins, and that's always going to be when your x is 0. That's your y value is going to be your initial value when x is 0. We're going to need a multiplier or a growth or decay factor, and of course we always have x. How are we going to find our growth or decay factor? Well, first we look at this and we go, oh, it's decaying, all right, 320, 80, 25, okay, it's decaying. So what we're going to do is you can pick any one of these. I'm going to pick 5 divided by 20. And if I do 5 divided by 20, I'm going to get 1/4, right? If you put that in a calculator, you could write it as 0.25. Okay, you could do 20 divided by 80. You're still going to get 1/4 or 0.25. All right, so let's move on to the next one. Once again, we're going to start with our initial value, and that's always going to be the y value when x is equal to 0. So that's -1. We've got I'm looking at this, -1, -3, -9. Even if the numbers look like they're getting bigger, remember they're negative. So this is actually another decay. So we're going to do -81 divided by -27, and we get a 3. Oh, I see. Okay. Because of our initial value being -1, it's going to look like it's actually a growth. It's a growth, but because our initial value is negative, in the table our values are going to be getting smaller and smaller. If we divide -27 by -9, we also get 3, so that is our growth factor. That's an interesting equation there. Okay, so that's another section. So far we had the initial value, rate, and factor part of the test, and then we had the context part of the test, and then we have the equations from tables part of the test. And the last part of the test are the graphing ones. And so to understand what a growth and decay looks like is really helpful, and I know that during the lesson you guys did that. And so we can also talk about what's important to know table-wise. It's really important to know, where is my initial value? What is my initial value? And when I look here, to find the initial value, I'm just going to plug in 0. I know this looks different than the equations we've been looking at, but to find the initial value really is plugging 0 in for x. And when I do that in my calculator, when I say 2 to the 0 power minus 3, I'm going to get a -2. That's my y-intercept. So I'm going to go ahead and put that there at -2. And then I know the general, because it's a growth, because 2 is bigger than 1, I know what it's going to look like, but I need to know where that horizontal asymptote lies so that I know where the tail kind of hovers over of the exponential. And so what I'm going to do is I'm going to see what happens when x is 1. So when we plug x is equal to 1, I get 2 minus 3 is negative. So we get 2 minus 3 is -1. So I know I'm going to have 1 and -1. And then let's just do another one, and then we'll talk. I talked about the tail, and I didn't write the horizontal asymptote at all. So let's go ahead and plug in 2, and I have 2 in there. 2 to the second is 4. 4 minus 3 is 1. So it's slowly growing. Let's put one more in there to see how it shoots up. When I put a 3 in there, whoops. When I put a 3 in there, 2 to the third power is 8. 8 minus 3 is 5. That's not really shooting up too fast, but you can see it's starting to. Now, where does the tail lie? The tail actually lies right here. And I say tail, I mean horizontal asymptote, where the tail will hover over. So I look at -3, and I know that if I went ahead and spent more time graphing, or spent more time making this table, if I would put numbers like -1 in for x and -2 in for x, the values would be getting closer and closer to this horizontal asymptote. I'm not going to spend that time because I just know that the tail of the exponential is going to hover right above the horizontal asymptote of -3, and then it's going to shoot up as we go to the right because it's an exponential growth. And that's all you need to show. It's just an understanding of how the table helps us and how our understanding of what a growth and a decay looks like. So I look at the 1/2, and I know this is a decay. So I'm also very interested, when I do my graph, in knowing where the y-intercept is and where the tail is. So if I put a 0 in for x, it's going to give me my y-intercept. 1/2 raised to the 0 power is 1, just like anything raised to the 0 power, it's 1. So 0, 8, yep, it's going to start up high. And then let's see what happens as we increase the x value. When I increase 1, well, that's 7.5, right? If I put 1 in there. So that's going to be 7.5. And then if I put 2 in there, that's going to be 7. Well, this will be interesting. We're going to have to do some other x's. But we're seeing what's happening as we're approaching our tail. So let's see, if I put a 2 in there, I have 1/4, so it's 7 1/4. You know what? I could continue this. Do you think I'm ever going to reach 7? No, because my tail, or my tail's going to rest on, or hover over, rather, the horizontal asymptote that's at 7. So I'm going to put my horizontal asymptote at 7. And I know that if I continued plotting points to the right, I would just get values that are getting closer and closer and closer to 7, but never quite touching it. And then if I really want to know what happens, let's say to the left, if I start plugging in -1 for x, I'll get, what, 2? 2 plus 7 is 9. If you put that in your calculator, you'll believe me. And so I can see that the kind of decay it's going to be is it starts up high, it comes down low, and hovers right over our horizontal asymptote of y equals 7. Okay. The next part is still the graphing, and we're going to do the same thing. We see right away that we can just go straight to this. We see that we're going to have a horizontal asymptote at -5, so I'm going to put that in. I know that my tail, the tail of the exponential function, will hover over that. And then I'm going to go to the table. Tables are great, aren't they? They can help us when we're not sure exactly how to graph. And so we're going to plug in a 0 for x. And I'm going to make sure that I am still going since I paused it. This is good. 0 for x, and that's going to give me a -4. So that gives me my y-intercept, right? I know that because it's a growth, if I go to the left, if I put a -1 in there, that's going to give me, let's see, if I put a -1, and that gives me 1/3, which gives me a -4 and 2/3. Okay, the point being is that I'm going to get closer to this horizontal asymptote, but I am not going to be touching it. But let's see what happens when we move to the right. If we make x equal to 1, I'll get a -2. So we can see the values going up as we're heading to the right. If I make x at 2, I get 4, if you put that in your calculator. And let's go one more. If I make it a 3, well, that's going to be, let's see, 27 minus 5 is 22. Can't fit that. So I'm going to go ahead and shoot it out knowing that that's really what it's doing. Okay, so here I don't see something that shows me where my tail is, which is interesting. I wonder what that means. Do you think that means that my tail is at y equals 0? I believe so. Let's go ahead and put it there. Okay, and let's go ahead and make a table and see what happens with the table. When I plug in 0 to find my y-intercept, I get 3. So 0, 3. Now this makes sense, right? We finally have a number in front where our initial value, like we're used to looking at the equation, our initial value is apparent, which is our y-intercept. Let's go ahead and plug in a 1 and see what happens. We get 3 1/4, right? So it's just going to, let's see, 1 is 3 1/4. And then we're going to put in 2, and we're going to get a little bit, let's see, we'll get 3 1/16. Oh, you know what? I should be multiplying. So hold on. That's not right. If I put 3, sorry, this is what happens when I'm not paying attention. All right, let's back it up a little bit. So when we put 1 in, we get 3 times 1/4, which is 3/4. Much better. So the y-intercept is here. And then when we go to 1, we get 3/4, right? When we go to 2, we would get 3/16. Okay, it's getting smaller and smaller and smaller. Do you think it's ever going to touch 0? No, it's not. Let's see what happens as we move to the left. When we put a -1 in, we'll get 3 times 4, which is 12. Oh, I see what's happening. It's going to shoot up on the other side. So if we read this from the left to the right, we can see it is decreasing, and we knew that because 1/4 is less than 1. And there you go. I think that's it. So this is the test that everyone is going to get a perfect score. Let's end the year strong. It's been a great year. Let's do great on the test. See you in class.